We will begin the chapter Electricity and Magnetism. Electricity is used to produce heat, light, and to make machines work. It is an important source of energy. Various common phenomena are related to electricity, including lightning, static electricity, etc. So the question arises, what constitutes electricity? Or what is an electric circuit? Or how does electricity flow in an electric circuit? Let us find answer to these questions.
Let us perform a simple activity. For this activity, we need a plastic comb, small pieces of paper, and a woolen cloth. When we bring a plastic comb near some very tiny pieces of paper, it will not have any effect on them. If, however, the comb is first rubbed with the woolen cloth and then brought near the tiny pieces of paper, we find that the comb now attracts the pieces of paper towards itself. These observations are explained by saying that initially the comb is electrically neutral, so it has no effect on the tiny pieces of paper. When the comb is rubbed against a dry hair or a woolen cloth, then it gets electric charge. This electrically charged comb exerts an external force on the tiny pieces of paper and attracts them.
Similarly, a glass rod rubbed with a silk cloth and an ebonite rod rubbed with fur also acquire the ability to attract small pieces of paper and are said to have electrically charged. Let us now understand fundamentals of electricity. Charge is a property of matter, just like mass, volume, density, etc. And it is a measurable quantity. It has been found by experiments that there are two types of electric charges, positive and negative. In order to move charge, we need charge carriers. Electrons and protons are charge carriers. Electrons carry negative charge, while protons carry positive charge. Neutrons are neutral. They have no charge. Electrons and protons carry equal charge, but of opposite nature. Charges exert force on each other, and that force is known as electrostatic force. An important property of electric charge is that like charges repel, while unlike charges attract each other. The SI unit of electric charge is coulomb. Charge on an electron is minus 1.6 into 10 to the power minus 19 coulomb, and charge on a proton is plus 1.6 into 10 to the power minus 19 coulomb. So you can see very well that charge on an electron is equal and opposite to that of charge on a proton. In this chapter, we will focus on current electricity. Current electricity is a form of electricity which makes all our electrical appliances work. This form of electricity exists when charges are able to flow continuously or constantly. In some substances, the electric charges can flow easily, while in others they cannot. So all the substances can be divided into two electrical categories: conductors and insulators. Conductors allow electricity to flow through them. Examples: metals, human body, animal body, and among non-metal, only carbon is one such substance which allows current to flow through it. Insulators, on the other hand, do not allow electricity to flow through them. All non-metals except carbon are insulators. All the conductors, for example metals, have some electrons which are loosely held by the nuclei of their atoms. Consider the atomic model of sodium atom. Sodium is a metal. In its balanced state, it has 11 protons in its nucleus, an equal number of electrons orbiting around it. Electrons orbit at varying distance from the nucleus of the atom. Some electrons are closer, while some electrons are far off from the nucleus of the atom. The electrons that are closer to the nucleus feel a much stronger electrostatic force of attraction to the center than those in distant orbits. The outermost electron of an atom is known as valence electron. This one is a valence electron. These electrons require relatively less energy to be ejected from the atom and creating a free electron. The presence of free electron in a substance makes it a conductor of electricity. So that is the main reason behind the concept of current, electricity in any substance. Let us understand the mechanism of current flow through a metal wire with the help of these two pictures. Let us assume we have a copper wire which is filled with countless number of copper atoms. In the first figure, when this wire has not been connected to any source of electricity, like a cell or a battery, then the electrons present in it move in random directions. These electrons are the free electrons. On the other hand, in the next figure, when a source of electricity is connected between the ends of this wire, then an electric force acts on the electron present in the wire. Since the electrons are negatively charged, therefore they start moving from one end of the wire to the other end. Please observe the SEM carefully. As the free electron is floating in a space between atoms, it is pulled or drifted by surrounding charges in that space. In this chaos, the free electron eventually finds a new atom to latch onto. In doing so, the negative charge of that electron ejects another valence electron from the atom. Now a new electron is drifting through free space looking to do the same thing. This chain effect can continue on and on to create a flow of electron called electric current. I hope you have understood the concept of electric current. Electric current is the flow of electric charges in a conductor such as a metal wire. And therefore, the magnitude of electric current in a conductor is the amount of electric charge passing through a conductor, that means through a given point of the conductor in 1 second. If the charge of Q coulomb is flowing through a conductor in the time t, then the magnitude of current denoted by capital I flowing through it will be I equals to Q upon T. The SI unit of current is ampere and it is a scalar quantity. As we have seen just now that I equals to Q upon T, therefore 1 ampere of current will be equal to 1 coulomb upon 1 second. This relation gives us the definition of 1 ampere, which is when 1 coulomb of charge flows through any cross section of a conductor in 1 second, the electric current flowing through it is said to be 1 ampere. There are other units of electric current which are smaller than ampere. One is milliampere and the other is microampere. However, there is one more unit which is called nanoampere. So 1 milliampere is equal to 10 to the power minus 3 ampere, while 1 microampere is equal to 10 to the power minus 6 ampere. Since charge on an electron is minus 1.6 into 10 to the power minus 19 coulomb, and if n number of charges flow or n number of electrons flow uniformly through a cross section of a conductor in the time t, then total charge flowing through the cross section of a conductor will be Q equals to Ne, and therefore I equals to Ne upon T. The number of electrons flowing through a conductor in time t so as to maintain the flow of current is then given by this equation. If current is 1 ampere and time is 1 second, and ignoring the negative sign over here, if we put all the values in this equation to calculate the number of electrons, then we get the number of electrons as 6.25 into 10 to the power 18. Hence, we can say that the flow of 6.25 into 10 to the power 18 electron per second through any cross section of a conductor constitute current of 1 ampere.